All right, welcome back, everybody. This is part 2 of our calculus video series. I'm the other guy that runs this channel, so nice to meet you. These videos are going to be likely done alternatingly between me and my peer. And yeah. So with that out of the way, I would like to introduce you today to several ideas, some of which you may already be familiar with. And I have these written out right here: the derivative, differentiation, rate of change, and the power rule. If you don't know what most of these things mean, that's okay, and also good, because then I can actually teach you something. So without further ado, I would like to first draw a linear function. This is going to be a straight line. Mark some values here. Let's say it's going to be this. Yep. Okay. Now, this straight line, this is represented by the function. You guys can see, right? Yeah. This is represented by the function y equals half x plus 2. This half right here, this 1 over 2 represents m, or gradient. And this just represents the y-intercept when x is 0. Now the part I want to focus on here is the gradient. You might have learned before that the gradient is the rise over the run. That's a pretty common way of explaining it to students. That means you divide this change in y value by this change in x value. In our case, it's 1, 2. But I want to explore this idea a little bit further, and I want to link it to the first topic of discussion, which is rate of change. Now, what is rate of change, and how do we really define it? How do we get our head around it? Well, this linear function right here is a pretty good place to start. We know that the gradient is the rise over the run, i.e., the change in y divided by the change in x. Now this might look a little bit weird to you guys. By the way, this triangle is a capital delta in the Greek alphabet, and it is commonly used to represent change in certain variables or values. And that is what the gradient essentially is. It is the change in y over the change in x, or their ratios, or however you would like to call it. And the gradient can also be it's also called a slope, and we can begin to link it to the idea of rate of change. What do I mean by that? Well, it's essentially almost the same thing, and it's pretty self-explanatory. The rate at which something changes is how fast it changes or how much it changes in, let's say, a given amount of time, or in relation to some other kind of variable. I'll elaborate a little bit further. That means that here, every time you have a change in y by 1, that then x will change by either positive 2 or negative 2. Yeah, that's pretty self-explanatory. And you can say that the rate of change of this function is 1 over 2. The gradient is 1 over 2. It's constant the entire time. It's a straight line. Let's define this. This would aid my explanation a little bit more if my pen would work. X can be all real numbers. So x, your input x here, is part of the real number set. So it can be pretty much anywhere, any number you can think of. That means this function is going to be straight always. And because you know that, you can say definitively that its rate of change is going to be 1 over 2. And measuring gradient, you can do it algebraically, but often we just look at units, values, numbers, and we can extrapolate the gradient from like that from straight line or linear functions. But this gets a little more difficult. This gets a little more difficult when we have curves or nonlinear functions. So I'd like to get into that part now. So I will draw a quadratic. Not the best quadratic function, but oops. Okay. All of a sudden, this becomes a little more difficult, right? For consistency's sake. Right. So all of a sudden, it becomes a little more difficult to determine the slope or the gradient of this quadratic. It doesn't have a holistic or overall gradient or rate of change, does it? Because here, at smaller values, when x changes, y is going to change by a very little amount. Just to put this out here. I just want to elaborate on this further. Y equals x squared. Let's say our x input, x1, is 0.05, right? And 0.05 squared, that's going to be our y output, is, I don't know off the top of my head, but that's 0.0025. So for changes in x, at smaller values, the corresponding change in y is also smaller. But as you get larger and larger x inputs, y is going to increase exponentially and specifically by its square. And this makes it quite hard for us at first glance to determine the rate of change at a particular point. Well, it's curved and it's got this exponential increase in y, and you're like, oh god, what do I do? And this is where we begin to go on to our second topic of discussion today, the derivative. So having already discussed rate of change, give me a minute. Yeah, so having already discussed rate of change using linear functions, let's say we want to also find a way to determine the rate of change of certain curve functions like a quadratic. But we're going to have to make alterations to our method, right? Because we can't just do this thing here as we did, because you can pick really any range on this linear function and you're going to get a gradient of 1 over 2. Doesn't really matter where you start, unless you, like, if you get the right corresponding values, then you should get a half each time. Here, that's not the case. If you try and do a similar thing here, keep in mind similar thing, or actually, I should say the same thing. Let's say you pick values 2. Could you draw? Thank you. 2 and 0.5, right? And you say, okay, rise over run. So rise is 1.5, and oh wait, no, it is not. The rise is 2 minus 0.25, so 1.75 and 1.5. And if you try and use the gradient like this, so yes, 1.75 divided by 1.5, it's gonna give you, God knows what that is in fraction form, excuse me, I'm not at the top of my game today. Yeah, it's 7 over 6, just to make it nice. This is going to be terribly inaccurate. You can see here that this straight line here, this straight line, or this straight rate of change this rise over run represents is veering off the actual curved path. The reason this curved path is such trouble for us because there is a difference in the rate of change along a range of points. That's our problem, because the rate of change constantly keeps altering, it constantly keeps changing, so we can't really nail it down that well using traditional methods. A similar method, though, you can attempt to find the rate of change at a particular point. That is not entirely correct. I will say why in a second. Is by using tangents. If you draw tangents to curves, tangents meaning it touches it at one particular point, then you can kind of extrapolate using this same linear method, the gradient at that one particular point. But the reason we don't really do that anymore at this level is because it's slow, it's inaccurate, and it's not really it's just an inferior method to the tools in calculus that we already have and that Newton and Leibniz already invented for us. So okay, but then what can we do to get around this problem? This is where I'm going to get onto the derivative, the second topic of discussion. And yeah, so it's nothing you should be really scared about. I'm going to draw a second quadratic function here. A larger one, maybe, if my pen would draw. I shouldn't have used the fountain pen for this. Here. Okay. It's going to be okay. All right. So I'm not going to draw any units here because it's going to be just kind of messy and inaccurate, and I don't really want it to mess up this explanation. Now, the derivative relates to this idea again, but it kind of develops on it. It kind of advances in thinking. So what we essentially want to do is find. Okay. Yeah. So our problem is that we can't really determine the rate of change of this curve at whatever x values we really want because it isn't linear. So we need to find a way to get around that. Now, what Newton and Leibniz thought were, okay, of a curve, right? Zoomed out, you can clearly see it's curved, correct? Because its rate of change changes. This is what causes our problem. Because it's not constant, therefore it's going to be, hard to really determine. But they found a way around this, that what if you zoom in, let's say there's a little magnifying glass here. What if you zoom in so far and pick a range that's so small, so tiny, it's in real life it'd be, like, realistically, it's much smaller than this. But what if you picked a range of x inputs that's so tiny that this curved line, the curvature, essentially fades out and appears to be perfectly straight? So when it's perfectly straight, correct, we can basically adopt this very same method we did earlier with the linear function. Because it's straight now, its rate of change. By the way, I'm using because it's straight now loosely here. It's not, but it practically is. And any deviations are practically, again, ignorable. Therefore, we apply this same method as we did with the linear of rise over run. It's the same thing. Rate of change of y over change in y over the change in x. Just this time, it's in an incredibly small, tiny range. You can do the same thing for linear functions as well. You can pick an insanely tiny range, and you will still get out a half from it. But it's much easier because, remember, the rate of change is constant, whereas with curved functions, it isn't. I'll just write out fx equals x squared. If you haven't seen fx before, this just means a function that turns an input x into some sort of value, i.e. your y value. That's all fx means, if you're not familiar with it. So yeah, going back to here. So yeah, so Newton and Leibniz thought, what if we make this change in x, this range super tiny, so that the curvature essentially dissipates and we get a straight line? Then we apply this rate of change idea. So that's going to look something like this. I'm going to begin the derivative idea now. Let's pick an x value. Let's say x1. And this is going to give us an output. Remember, we're using x squared, just the basic quadratic function. x1 is going to give us x1 squared, or just x1 squared. Subscript, I'm just using it because why not? And x2 is our slight nudge, this very small nudge in our original x1 value. It's going to give us x2 squared, or is this. Now this is better denoted when we use something like h. You can either do this, but I wouldn't really recommend it because this is not very widely used. X becomes x squared, and x plus h becomes brackets x plus h squared. This is how we commonly denote this very small nudge, or this very small change or alteration in x. This here. And I want to link this this idea to limits now. In last video, my peer explained limits, and I'm going to be assuming here that you are familiar and are comfortable with the idea of limits, and maybe even know how to compute them. I apologize, I maybe should have said this at the beginning of the video, but regardless, here it goes anyway. If we limit h to 0, then this all begins to line up somehow, right? If we limit h to 0, then we essentially have that extremely small change in x here. And this is the y value it provides us with. And remember how I said that at that small of a range, the curvature dissipates and essentially becomes a straight line. So we can apply this idea of change in y over change in x. And that's exactly what we do. The formula looks a little bit different, but it's essentially identical. So the way we denote this is the formal equation for first principles, or the derivative. Fx, so function of x, limiting h to 0, f x plus h minus f of x divided by x plus h minus x. Appears I need to change pens real quick. I'll be writing in black now. Okay. So we have this formula here. This looks a little bit intimidating. I hope you can see it reasonably well. I apologize if you don't. I may write it clearer up here. So fx limit h to 0, fx plus h minus fx over x plus h minus x. This is essentially the same idea as the change in y over change in x, because we're taking I'll use the visual aid for this. Because in order to find the change in y, we need to subtract, take the difference of the larger y value, this being x plus h brackets squared, because x plus h is our input now. Imagine it as its own x input. So we're taking the larger value and subtracting the smaller value, and then dividing that by the difference between the larger x input and the smaller x input, which is x plus h being the larger minus x being the smaller. This is identical to just change in y over change in x. And this is essentially the derivative. It's really this easy. I hope the way I've explained it makes it seem or is easy for you to understand. But this is what it's about. This is the derivative. And this is where calculus all opens up into this beautiful world of math and cool things, and you will hopefully get into areas like multivariable calculus where this all blows up and just like what is going on. But trust me, it gets really, really cool. Now I want to further develop on this idea of the derivative and give you a better feel for it. So this explanation that I've provided you is using functions and using graphs mainly. Graphs, they're going to be the main focus or a main focus in your calculus careers in school and likely otherwise. Graphs are very, very commonly used in differentiation because they're very easy and we've just adopted them. But I don't want you to inherently have this idea that differentiation and the derivative and rate of change is only related to functions and graphs and lines and curves, because it isn't. You will find, you will maybe come across different scenarios where you don't have graphs and you have to differentiate. I'll explain what that means in a second, and use a derivative and rate of change where you don't have graphs and where you only have values. So this is just the visual explanation and is going to really aid you in your understanding of calculus and the derivative. So with that in mind, I would like to move on to what differentiation really is. Now, this formula here that I've written out, this is formally well known as the first principles formula or equation. And it's kind of the root of differentiation, at least the way I know it, is just using this idea of rate of change and change in y over change in x. And it's got this like algebraic almost magic that it can do. Now what do I mean by that? This first principles formula is very useful to us in understanding. We don't apply it because it's inconvenient and long and will take a lot of time, but it's very useful in understanding because it essentially describes generally that if you input a function and you want to find its derivative. Okay, so what do I mean by that? Why is this some first principles equation here so useful to us, at least intuitively or just in general? Well, it allows us to find the differential or the derivative of a function. Now, what are those two things? What do those do? Something pretty cool. So the differential of a function essentially allows us to find the gradient or the rate of change at a given x or given input variable. Now, to help you out with that, we have x squared, correct? And the differential, which is denoted by this dy over dx, is 2x. That means if we input, let's say 3 into this 2x, so 2 times 3 is 6. At that x value, that corresponding x value on this curve, we're going to have a rate of change or a gradient of 6. Now this is like crazy useful. This is really, really cool. You might be wondering, okay, well, how do we exactly get this 2x? Where does this come from? Aha, and now this is where this first principles formula comes in. First principles essentially allows us to prove what the differential of a function is, and is like kind of the root method. It's like the bareback method of proving this. In practice, we never use the first principles equation because it's very long, very cumbersome, and just impractical, and there's no point because we should already be familiar and know what that is, and so does the examiner know that you know. But for videos like these, it's like absolutely perfect to explain how to find a differential and what a differential really is. So, okay, how can we go about doing this? Well, according to the formula and according to what I said earlier, we need function of x plus h. So in our case, fx equals x squared. That means on the top, of course, we're going to limit h to 0. On the top, we're going to have x plus h squared minus x squared divided by x plus h minus x. You can simplify this to be x squared plus 2hx plus h squared minus x squared, all divided by h. Now, these x's cancel. 2hx plus h squared divided by h. And now we've kind of got a problem. There's going to still be a remaining h term even if we divide all this by h. But here's the catch. This is it's not really a trick. It's more of a mathematical loophole we have here. This h squared right here is completely ignorable. Why? Because we've limited h to 0. H is already an infinitesimally small change in x, correct? Therefore, if you square that minute, insanely tiny change in x, it's going to be even smaller, to the point where its existence can be ignored entirely. So we ignore this h squared. As a general rule, if you try and prove differentials in first principles, then you ignore any h term with powers that are equal to or higher than 2. So with that in mind, it's going to be 2hx divided by h, and then the h's cancel, and then you just get this 2x, right? And that's the differential of x squared. And if you're still a little bit unclear on what the differential really is, or derivative, potato, the differential allows you, in our context, I'm going to only apply this to our context, the differential allows you to find the rate of change, or the gradient, or the sensitivity is a very good way to think about this. The sensitivity to change of a function at a given input, or in our case, a x value. So that means if we input like x is 2 or x is 3 on this graph and on this curve, this line, we can then tell with this differential equation what the gradient will be at that given x input. And that's why the differential, the derivative, is so very useful. This expands into so cool cool things. But for now, I just want you to really hammer this fact home into your heads. So we've covered rate of change, the derivative, and differentiation in basic concepts. Now I want to move on to the power rule. Now, if you're a real pattern seeker, then you might have already noticed, hold up, maybe just by coincidence, this x squared looks similar to this 2x. It's differential in the way that the power just kind of moves down. The power kind of just moves down to be the coefficient of x and kind of disappears, right? Aha. All right. Let's test our theory, this like lingering thought. Let's say fx is x cubed. First principles. Limit h to 0. X plus h cubed minus x cubed divided by x plus h minus x. X squared plus 2hx plus h squared times x plus h minus x cubed over h. I will turn the page, or rather get a new one. So this is going to simplify out to be x cubed You see my, okay. X cubed plus 2hx squared plus h squared x plus hx squared plus 2h squared x plus h cubed minus x cubed, and then all that divided by h. Now this looks pretty nasty. This is pretty gross, right? But remember that loophole I pointed out earlier. That anything equal to or equal to 2 or higher than, that doesn't make sense. Any power that is equal to 2 or higher than it of h can be ignored. So if we just put this all together, just so this makes sense, x cubed plus, we have plus 3hx squared plus 3h squared x plus h cubed minus x cubed. These x cubeds cancel. These h squared and h cubed terms are ignorable, and because such a small term multiplies x, x is also going to just from here, and h cubed is just, yeah, you just bye. So now we end up with 3hx squared divided by h, which is just 3x squared. And you're like, huh, okay. Now if you're also like really smart, and again, pattern seeking brains go beep boop 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 ticking, then you're like, we had x cubed, and now it's just become 3x squared. Again, the power is kind of moved down here to be its coefficient, but this time you have a 2. And you're like, aha, wait. X squared's differential is 2x. Coefficient moves down, but the power is 1, right? But we just ignore the 1. We never put it there. So you're like, oh, wait a minute. This might be actually kind of cool. This looks like it works. And you're right. Yes, this is a rule. This thing, what we've just done here, what we've just seen here, this little pattern, we can use a shorthand method here. This is pretty much what it's going to be. This is a shortcut of differentiating things that have a higher power than 1. It's called the power rule. So if you see a function, fx, like, let's say, 3x to the 54. This is extreme. I'm never going to see something like this. Differentiating this in first principles is pretty close to hell. It's not nice. It will take you pages upon pages upon pages of arduous, painful work. You might not, it will likely take you days to do this, if not a whole day, or yeah, days. And the power rule is good here, because this pattern that we've just noticed, maybe it would have been useful if I'd done a third one, but whatever. I don't want to expand to the power of 4. Don't really want that. I'm just going to skip to it. The power rule is awesome here, because we've just proved that if we differentiate with first principles, so, you know, the bareback core concept thing, of a function like this, then we can basically, we notice that the power moves down to be the coefficient of x and minus 1. You subtract 1 from the power, so it becomes 53 here. Same thing here. X cubed, 3 goes down to be the coefficient, so 3x squared. You basically subtract 1 from the power on the top, so it becomes 3x squared. Here it's the same thing, but here it's a different case because we have a 3, right? If you already have a coefficient, then the power is going to come down, so 54 times 3. The two coefficients are going to multiply. So any pre-existing coefficient is going to multiply by the power that's coming down times x to the 53. And this is your differential. So 54 times 3 is God knows what. Yeah, 162 x to the power of 53. That's going to be your differential of this function right here. It's that easy. That's the power rule. Now, to like leave you off with some sort of, you know, something to like think about is other methods of differentiation. Like, how do we differentiate this function, for example? 2x plus 3 to the 4, in brackets, of course. Or 3x plus 8 times 8x plus 12 to the power of 3. How do you differentiate that? Or something like this. X squared plus 6x cubed divided by 7x plus 4. How do you differentiate something like that? These are all different, and I'm pretty sure all of these can be proved with first principles. But you're going to see many, many, many more methods of differentiating all kinds of functions, and there's going to be a lot of color in this area of maths, in calculus. So this hopefully is a good segue and a good setup for the next video that my peer is going to do. What's going to come next is either going to be relating to these that I just left you with, or something else, but that is still in the works. So just to summarize, we covered rate of change, the derivative, what it is, what it does, why do we care, what it's good for, differentiation, and the power rule. And hopefully I've provided you with some intuitive thinking. I've maybe cleared up some gray areas for you, and I'm happy to have been of any help, if at all. So thank you for watching, and we'll see you in the next video. Goodbye.